looks like everything is working.
Yeah, that's
and
great.
Oh, people are clicking the button and they're popping in.
All right.
All right. Yep. All right. Well, I guess let's get this thing started. Hello, everybody. Welcome to today's webinar. Thank you for attending. For those of you who have seen our videos and attended our webinars before, you've heard time and time again about how all electric heat pumps perform in cold climates. And we've shown you some charts, some graphs from the manufacturer backing up these claims. We decided that wasn't good enough. And Tom created his own scientific study, and the results are in. He's going to go over those results in a second here. But first, just wanted to give you a reminder that we will be taking questions at the end of the webinar. You can ask them at any point in time just by clicking the Q&A button or the chat button at the bottom of the screen, and we will get to them at the end. So, Tom, what did you find out?
Let's get this sharing going on. So, hey, everybody. Well, I can't see you, but nice to be seen again. I have shared lots of manufacturer documentation with all of you about how cool this, no pun intended, this heat pump is. And so we wanted to do a little field study. Now it's a little field study, and I'm in some ways I'm kicking myself because I found out that we had these power meters at work, and then I was reminded. And so we should have been doing this monitoring over the course of the winter, and I wasn't smart enough to get that going. On the other hand, we found it. Well, what was that, Eric?
I was just going to say, but that means there might be part two.
Right. But we did find a week where we had almost a full winter simulated. We got all the way down into low temperatures. It's just a few weeks ago, and all the way up until maybe we don't need the heat pump at all. And so what is the point of all this? Well, probably all of us have furnaces in our houses. And yet every time we get on the news and we talk about climate change, or we hear a report, and it's mentioned often that air source heat pumps are going to be the method of heating our homes going forward. And the manufacturer data looks, okay, well, it works pretty well here, and it does this. We wanted to get a real field test and see how it performed. And so we're going to share those results with you. And, some of it's good, some of it's an education. Definitely there's more to follow up on. But so I guess one way to look at this is we're learning together. So let's continue learning. All right. So what do we want to find out? Well, number one.
Are you sharing your screen?
What was that? Am I not sharing? Oh, I'm not. I thought it was. Just a sec. Share screen.
I know that everybody probably would just love to look at us, but
there we go. Absolutely not. That's a little bit better. Okay. Thanks, Eric. Okay.
No problem.
This is the slide I was referring to before. So asking ourselves questions and trying to answer them. How are we going to do? Are we going to be able to hold space temperature? Are we going to be, holding it at 60 degrees in the space? That would be bad. That's important. And then number two is we have two different scenarios, which we'll talk about. Both these systems are well documented on our All Seasons Heat Pump website. So you can see these units getting installed. But how much backup heat got used? And then let's take a look at how often the backup heat was running. We wanted to see how much we could learn about defrost cycles. And then finally, how is this heat pump working in tandem with the furnace? In some cases, looking forward, we'll be replacing our air conditioner with a heat pump, and we'll be using it in tandem with the furnace. In some cases, we'll be going to all electric solutions. So in this particular case, we get to model both, which makes this kind of a fun study. All right, so here we go. Here's our test site. If you've seen our videos before, this is the test site that we did our first install on. This next picture makes it a little bit clearer what's going on. So there's an older house and a newer house. The green is the older house. It's smaller. It's also quite a bit leakier. So the contractor that came in worked with us and gave us an estimated load. Now, granted, and a little bit funny is, he was nervous about using an all-electric heat pump system. So I imagine he was fairly conservative in his heat loss estimates. So on the right side, the older home, that was heated by an oil furnace. And what we did was we pulled out the oil tank, we ripped out the furnace, and we have an all-electric solution on the green side, the west side. On the east side, because the load was more than the heat pump could handle, we decided to try out a dual fuel system on that side. So when the heat pump can't supply the amount of heat required, the heat pump comes off and the furnace kicks on in heating mode. And in the cooling mode, it's of course all air conditioning. But we're just talking about heating today. That's where the bigger challenge is for cold climate heat pumps. Okay, so that's what we're looking at. Here's a picture of the installed heat pumps. This is obviously a beautiful summer kind of a day, but this is when the heat pumps are really going to be doing their work. So we got some pictures of that. They're mounted on the north side of the house. Okay, so here's our east unit. So we've got our cold climate heat pump mounted outside. This is our dual fuel arrangement. So the owner bought a new Daikin furnace. And then above that is our heat pump coil. I'm not sure. Can you see my mouse moving around? Eric? Yep, good. Okay. And then so yes. Maybe not these dimensions, but the cold climate heat pump, or just basically the heat pump coil is installed right above the furnace. Okay. And on the west side of the house, this is the smaller side, we have a vertical air handler. You can't see all of it, but at the discharge of the vertical air handler is our electric resistance element. This one's sized for 8 kW, so it's a fairly, what I would say, is substantial electric heater, but also keeping in mind that we don't anticipate it to run very often. And so here's the guys from Professional Services today installing it. So that's what our setup is for our test. Now, so all we're using here is just a clip-on current transducer and then a data logger. So this is the power monitoring side of it. And for the temperature, we're going to monitor the inside temperature and the outside temperature and relative humidity. It would have been nice to have two of these. We just have one because there were two systems. So we kind of have an average temperature of what's going on in the house. Okay, so here's our service tech, Zach, clipping on. You can see this is the really, if you go down into this basement, it's something else down there. It's something out of Silence of the Lambs for those of you who are old enough to have seen that movie. Anyway, yeah, so he's just clipping over the lines, and we're going to meter. Now here's what we're metering. We're metering the east heat pump in totality, so not the individual fan or the compressor. It's the whole heat pump outdoor unit. We're also monitoring the west indoor air handler. So that's the air handler is basically the fan that pushes the air through the system, and then the electric resistance element going on at the same time. And then the west heat pump. What we are not monitoring is the furnace. We didn't feel like it was necessary. And then also we're monitoring the outside and inside air temperature and the outside air humidity. Okay, so why do we pick this particular week? Hopefully you all can see this. It's a little hard to, going back and getting historical temperature information for the city of Saukville is not easy to find, but I did find it. And so if we can just follow along why we picked this week, we started monitoring on Friday the 11th. It was cool, right? But then Saturday morning, we dropped all the way down to 3 degrees. Now, yes, this heat pump works colder than 3 degrees. It just happened that those are the temperatures available over the course of the week. So then our temperatures climbing up into the 60s, and then kind of settling into a typical mild weather climate for winter in Wisconsin. Okay, so what do we see? I'm going to leave this up here for a few minutes so you guys can admire this graph and try to make heads or tails. So I'll just give you a couple seconds to look. So what we've got in gray is our west heat pump cycling on and off and on and off and on and off over the course of the week, right? As we're taking simultaneously a look at this outside air temperature in blue, right? So we're going up and down with the days. And at the same time, this brown is our air handler with its electric heat element engaging and then shutting off, and engaging and shutting off, and engaging. So we're looking at this data and going, oh, that's interesting. You know, what story can we make out of this? Oh, and also notice that our temperature, this is our inside air temperature. So I don't know, the Zoromskis apparently don't like it very hot because we're just holding it like 68 degrees. More on that in a minute. So let's take a look a little bit. The first question that we're asking ourselves is, how much is the electric heater on? So it's on, and when is it on? So right out of the gate, when it got to be down at 3 degrees, the electric heater did engage and engage for 74 minutes. And then over the course of the week, it engaged for another 20 minutes, 2 minutes. And we can tell because the fan itself, when it's on, only requires 4 amps to run. And you can pull this off this middle data. And when the heater is on at 8 kW, and you just do a little bit of math at 240 volt single phase, the heater will max out at 37. And then the heat pump runs at 18 amps. Okay, so we'll take a look at this in just a little bit more depth on what it means. So this is our 3-ton model. This 36 is 36,000 BTUs. So our heat pump, we're going to go nice and slow through this. Our heat pump produces about 25,000 BTUs, which is about, we're just doing some math here, 4,320 watts. So I'm looking at this 25,000 BTUs. We were at 3 degrees, right? So I'm using this data chart saying, all right, to be safe, let's use this -5 data bin. So it's going to produce 25,000 BTUs, roughly 4,600 watts. Our COPs dropped because our efficiencies dropped, right? But it's producing a lot of heat with relatively low amperage. Now, at the same time, that trim heater comes on, it produces 27,000 BTUs with double the amperage. So this is part of the reason why we want to make sure our cold climate heat pump is working through as much of the winter as we can, because we have to double our power. Now, if you can imagine, if you had a heat pump that shuts off at 5 degrees or 0 degrees or whatever, what have you, well, then you're going to be running, instead of 18 amps throughout a lot of the winter, you're going to be running this full load, which is going to double your electric consumption, while at the same time also running the heat pump simultaneously. So that's not good. So we want to really minimize that electric heat backup. So here's what we're drawing from it. As we're looking at the data, the air handler is 4 amps and the heater is 33 amps, and it's powered by a 50 amp circuit. Our outdoor unit runs at most 21.6 amps. It's on a 35 amp circuit. And for this west side, which is our all electric side, the heat pump and the electric heater run at the same time. So as I'm looking at this and I'm thinking back about the decisions we made, we probably could have gotten away with a smaller trim heater. Now, does it make sense that we use the bigger one? If we were doing a multifamily building and we had to assign trim heat to every apartment, we want to look at this very closely. But for this house, well, they had to go through an electrical upgrade anyways. They didn't have air conditioning in the first place. So they had to do that. And since it was a new installation, we wanted to make sure that the house was going to stay warm before we worried about the efficiency of it all too. So we're taking a look back and seeing what we could have done better. All right, so that was fast and furious. Let's keep looking. So now, over the course of the week, it is my guess that this was on because of our cold climate situation. But with the temperatures here, it seems like this would have been a time that defrost cycles ran because we weren't under the capacity of the unit. So it looks to me like our electric heater is kicking on in place as the unit's cycling through its defrost. That's the assumption that I made. And here's how long these alleged defrost cycles were running. 17, which is kind of like what you see online with how long does a defrost cycle run. And in defrost cycle, what are we doing? We're running the heat pump backwards to push the heat out to melt the ice off the outdoor unit. And we'll probably have another webinar on that topic in its entirety. Okay, so these are the assumptions that we made. This is, again, what a heat pump, if you haven't seen this before, this is what a heat pump looks like when it's in partial defrost. So usually in a full defrost, this thing would be completely iced over. But we can kind of see that it starts at the top of the coil and works its way down for the frost. Because when the refrigerant is boiling inside, when it comes back as a liquid, I think that's where it it'll see frost and then work its way down the coil. So again, this is what the indoor air handler looks like. Its components, and this electric heater is sitting on the top. So defrost cycle comes in all sorts of conditions, but over the course of the winter, as the temperature drops, the relative humidity is always, seems always to be fairly high. So we could be running defrost cycles down to 10 degrees all the way up to 40 degrees. All right, so if we just look at the air handler now, this is our operating time. So when it's at 4 amps, this is when we're either defrosting or reheating. So over the course of the week, the air handler ran most of the time. If we look at the electrical usage, our total power was 101 kilowatt hours. So at 13 cents, it was like $13 to run the fan and the heater over the course of the week. Not terribly expensive, but not free either. Okay. And if we sorted it, you can see that this electric heater really ran for just a very short period of time. We already had the totals, but just to put it in sort of a relative perspective. And then the fan was off for half the week, which would be typical for a Wisconsin winter as well, over the season. Maybe not January, but over the whole season, we'd be cycling on and off, and we'd be on half the time. All right. And then as far as the West heat pump, so this is, again, the all-electric heat pump. This is just the heat pump on and off and on and off. So yes, it is a variable speed heat pump, and we're getting different cycles, but a lot of the time when it's cold outside, it's either on or it's off, right? And if we sorted that over the course of the week, we can see that a lot of the time the heat pump's off, and a lot of the time it's in, well, not a lot of the time, but some of the time it's in some partial load condition, and some of the time it's in basically full load. So over the course of that week, we used about, what I did was I took an average of all these data points, came up with an average of 8 amps times 240 volts, 1920 watts. Over the hours that it ran, it was 336 kilowatts for about a week. So end of the world for utility costs? Not really. And again, or maybe not again, but this heat pump's been in operation. Well, obviously you saw some summer pictures, made it through its first winter. And if I'm not mistaken, Saukville got all the way down to -12 for some time. So we did fine. I talked to the owner regularly. They're very happy with the heat pumps that they've got. Okay. Now, this is the whole like, hey, let's not ship anything till it's perfect. We started looking, the data didn't make a ton of sense to any of us because we couldn't figure out why the defrost cycles seemed to have like spacing that was almost equal. And so these aren't defrost cycles at all. And sorry to like lead you and mislead you, but this is kind of how we came up with the information. We had it all figured out, and then we had to look back again. So what happened was, turns out that the owners run night setback, which I don't know that we should have or shouldn't have told them, but they set their thermostats back to 60 some odd degrees. You can see at the temperature chart that it's dropping, right? So they're down, let's assume that it's maybe 63 degrees. And then at 7 o'clock, they go, oh, let's turn the heat back up. So what happens is it's just a regular heat pump thermostat. It's not like a Gree thermostat. It's Honeywell heat pump thermostat. It's a really nice one. At any rate, the heat pump comes on, and it's not like a furnace where it's got all this extra capacity. It's got enough capacity to meet the load. And so after a couple of minutes, the thermostat says, hey, we're not meeting the space temperature. So we turn on the electric heat. So what a shame. So here's when we go to the actual source data where we've got this all time. We've got the time and the power and the outside temperature and all that. So at 7 o'clock every day, the thermostat's saying, all right, let's run it back up to 70 degrees. And then after 1 or 2 minutes, the electric heat engages to keep us going. So no doubt that on Saturday it got down to 3 degrees in the morning. It needed the electric heat to keep it, to get to space temperature. But had the electric heat been running, I'm sorry, let me back up. Had the heat pump been holding temperature, this 78 minutes would have been a lot shorter. Now on Sunday, it only took 17 minutes to bring the space back to temperature. Odds are that on Sunday and on Monday, 16 minutes, and maybe even on Tuesday, and definitely on Wednesday and Friday, we wouldn't have needed to run the electric heat at all. So I thought that those were defrost cycles given the amount of time that they were running. Turns out that was just the thermostat trying to keep up with the space. So if I boiled this down, so we've got what, 78 and what is, maybe 150, maybe 200 minutes. We probably could have boiled this down to maybe 20 minutes of electric heat use when it was down at 3 degrees. Now we'll have to do some more experiments, but we wouldn't have known that had we just, had we not done the field test as is, right? So we're always trying to learn new information and disseminate the information that we've got. So lesson learned, right? Don't run your heat pump on day and night. It's not going to save you any energy. It's probably going to cost you more. Okay. So now let's go back to the defrost cycle discussion. What I learned is that the defrost cycle doesn't require that the trim heater be engaged. So if the space thermostat's satisfied and we can initiate a defrost cycle, it happens without anybody knowing about it. So maybe a discharge air sensor would have been necessary, but the fan should be shut off. So we're going to have to work on, there's a 4-way valve on the top of the compressor. If we can monitor the reversing valve, that'll probably be the best way to go going forward for monitoring. Okay. Number 3, we should not be setting that heat pump stat back. If the owner wants it cooler, maybe they should open a window. But it's something to consider because you're paying a bigger penalty, or maybe the heat pump stat could be programmed to slowly bring the temperature up. I think it's fairly common knowledge that heat pump discharge air temperatures aren't as hot as what furnaces are. So it takes a longer time to get up to temperature. The last little piece is that the thermostat does not control the outdoor unit. There isn't any connectivity between the outdoor unit and the indoor unit. So we're still trying to figure out some of these pieces about how does the fan know to shut off when a defrost cycle is initiated. And we're actually, it's a little funny that we are still working on this little detail. So we think we have it, and I'm going to show you something next that makes me think we have it, but I'll show you here. I'm going to share something else. Let's see. Eric, are you seeing my spreadsheet or do I need to reshare?
I do have to take it off of mute. I am seeing your spreadsheet.
Okay, great. So this is how the raw data came out. So we've got, if I can go again super slowly, at 0 minutes, so we're just hooking up our meters onto this equipment. It appears, so, and let's go a little bit slower. The west heat pump is the all-electric system. The east heat pump is the one that's tied to a furnace, and it looks like it's just off or we haven't hooked it up yet, okay? So 0.1 amps is telling us that the controls are running and that's it. On the air handler, same thing. The controls are running and that's it. Could be that we started off, so we're going to be looking at this column B, and we're going to be looking at this column I, and then I've just added this data. I'm a little, it was a little tricky because we set our temperature and humidity at 5-minute increments, and our power monitoring at one increment, so I couldn't cut and paste, so I had to do a little bit of handwork to get all this information in. So it would make sense that at 33 degrees and 50% relative humidity, that we might be running a defrost cycle that ran for 10 minutes. Now, minute 10, which is 10:25 in the morning, now our fan is running and our heat pump is running, and we're, somewhere in this area, on the time grid. So we're at a cooler temperature, so it makes sense to heat. And then we run another defrost cycle for 14 minutes. Now, this is, again, we're going to revisit this data at a webinar down the future. This is what our best guess is. And then it's off. The defrost cycle is off. We're back to running our fan. We're back to running our heat pump. Now, remember, it's getting colder outside. So we're, again, defrost, again, heating, again, defrost, again, heating, again, defrost, again, heating, cycling and cycling and cycling. And then we get to a point where, okay, now we're just running. And it's because it's colder outside. And I didn't plot all the temperatures on this, but we know from our original grid that it was getting colder and colder. Well, it makes sense. As it gets colder and colder, the relative humidity outside is dropping. And so we're going to have less moisture to freeze on the coils. So we're running for a long time in heating mode. Now notice our heat pump's changing its capacity. Sometimes it's nearly full at 18. Sometimes it's down at 8. We're just matching our load. Oh, little defrost cycle at what time is this? This is at 4 in the afternoon. Again, a long period of time that the heat pump's running. At one point it turned off over here. And then some more defrost cycles. Now we got some data later in this spreadsheet where it shows the heat pump defrost cycles running a little bit longer than I would have anticipated. So we want to just kind of play that out. But it seems like typically the defrost cycles are 5 to 15 minutes, which kind of matches what you'd find in just doing defrost cycle search on the internet. The mechanics of all of it, regardless of the heat pump, are the same. Trying to boil refrigerant in a cold climate, we're going to freeze the moisture that's outside on the coil. Okay, so I'm going to go back to the presentation and share from current slide. Okay, so roughly 10 minutes for defrost cycles at different times. We saw defrost cycles all the way up to 40 degrees and all the way down to 15. So again, more on that in coming weeks. Now that's just the west air handler. Here's our east unit. Now what's interesting about the east unit is the load was significantly bigger on the east side of the house. Yet, other than this period here where we didn't really need the heat pump to run at all because it was like 60 degrees outside, the heat pump just about covered the whole operation without the furnace running. So even though the capacity on the heat pump was only 36,000 BTUs and the load was 72, for whatever reason, we were able to have that heat pump running and holding throughout most of the week until it got warm. It looks like here when we're down at 3 degrees that the heat pump actually shut off and the furnace was doing the work. But then it seems like the balance of the week we were running. So over the course of the week, at least half the time, and I know if we compared it to the west heat pump, that one was off a significant part of the week as well. So my guess is that 3/4, 80%, maybe more of the time the heat pump met the load of the space. Okay, so we're coming up to the end of our presentation here, at least with the facts and the figures. So what do we learn? Now, number one, and probably the most important thing is, in a cold climate situation, is this particular heat pump going to hold up? Absolutely. Do I feel like it would have held up at -15? I do, because the mechanics of this heat pump, which we've covered in other webinars, it doesn't really care how cold it is. It's just managing this four-way valve to deal with the colder climates. Okay, so did it hold temperature? It did. And had we not had the morning warm up, it probably would have performed a little bit better. Now, how much backup heat was used? The West heat pump used 101 kilowatt hours over the course of the week. And my guess is it would have been about, well, I did that wrong, sorry, kilowatt hours. Probably would have been 10 to 20 over the course of the week without the morning warm up, had we held the temperature and not let it drift down. Cost impact for backup heat, 101 kilowatt hours, and for just the trim heater, and 336 kilowatt hours for the heat pump. Now again, we'd have cut this down significantly, the 101 kilowatt hours, had we not done the night setback. How long are the defrost cycles running? Typically 10 minutes. Some were longer, some were shorter. Again, more investigation on our part. And finally, how do we do in tandem with furnace? The West heat pump and the East and the electric heater were 437 kilowatt hours. The East heat pump, for whatever reason, did not require as much energy. We were backed up by the furnace when it was the coldest outside. So, is it a perfect field test? Absolutely not. Is it interesting stuff? I think so. Am I more confident that these cold climate heat pumps do what they say they're going to do for this particular brand? Absolutely. So what does that mean for you as contractors and engineers? Well, number one, if you're retrofitting something like a historical space and you've got electric there, but you don't have gas or hot water, use this heat pump. You can make it through a winter. It seems like pretty definite. Number two, for multifamily buildings, and our last webinar touched on that, getting rid of the gas in the vent and all the labor and materials that go along with it have a big advantage. And we can see that this heat pump's going to hold up under cold climate conditions. And then finally, for those of you who are trying to decarbonize, this is a legit way to do it. A dual fuel is a good way to go. You don't have to go all electric to get the benefits of it. We saw on the East heat pump that we covered most of the theoretical winter by using the heat pump, which should, pave the way for us doing more renewables. And that's my last slide. So, Eric, if we haven't put them all to sleep, we can open it up to some questions.
All right.
And I'll leave my deck up in case we need to go back to something.
All right. That sounds great. Yeah. So we have at least one question that's come in so far. Again, if you have any questions, you can pop them into the Q&A or the chat windows, and we're monitoring both of those. Before we get to this first one, so I've lived in Wisconsin my whole life, and I think that temperature thing that is happening where you drop it down like 8 or 9 degrees at night, that's pretty typical here, right?
It is pretty typical. And, for example, Focused on Energy encourages us to set back our thermostats at night. What they don't really explain is that when you're heating a home, or particularly when you're heating a home, you've got the air that's not at the right temperature, but also all the objects in space. So you introduce your warming air into a home or an apartment or whatever it turns out to be, and you have to reheat all those objects in addition to the air. So it can take quite a while. Some of our, one of the things you can do with a building is cool it down over the night, and it's like almost like mass storage, where the objects will retain the cooling, and then when you have to run air conditioning, you have less of a load by having a cooler building in the morning.
Okay. All right. Just an observation. Anyway, so we've got one here. I'm assuming you could pair this with a natural gas furnace. Have you looked at the economics to optimize changeover OA temperature from all electric to NG trim heat, natural gas?
It will always be cheaper. to use natural gas, it's basically I can't say it's subsidized, but when just raw creating BTUs with electricity and a heat pump, well, let me do it a little bit slower here. If we're going to create electricity or heat with electricity, like a resistance element like we saw in the heat pump, that's about 3 times as much energy as the average output of the heat pump. So when we go from electric resistance to heat pump, somewhere in there is like 2 or 3 times more efficient that the heat pump is than the electric resistance element. When we go to gas, if the heat pump is really knocking the ball out of the park, it will be close to gas. It'll never catch up to gas because gas is just so cheap. So right. The idea would be, well, let's say you replace your air conditioner at home. Can I make up enough in air conditioning mode going from 13 SEER to 18 or 20 SEER and make it up in air conditioning mode? And the answer is yes, or very close. So then what have we got? The ability to use renewables. So if you have solar panels or that kind of thing, you're putting those 2 pieces together, and then you have an opportunity to do some savings. Does everybody want to do that? No, not everybody wants to. But if we look at the coasts, there's all sorts of incentives for people to decarbonize. And those incentives are going to be pushing from the outside of the country into the middle of the country eventually. If we were going to just look at the upper Midwest as a country, we're the 5th largest gas user in the world. This is according to the folks at Fresh Energy in Minnesota. And I repeat their information a lot because Minnesota is really far ahead of us as far as their grid quality and producing less CO2 for every kilowatt hour produced. So heat pumps make more sense in Minnesota than they do in Wisconsin as of now. I hope we catch up.
Okay. All right. Another question. This is about the air handler. How does the air handler know to turn off during defrost on the electric system?
That is the question that we need to answer in the next webinar. We think we've been going back and forth with this with the manufacturer, and we thought we had it, and we didn't have it. You know, it's just a standard heat pump thermostat. There isn't any connectivity that we can figure out between the outdoor unit and the indoor unit. It would have to pass through the thermostat, and it's a standard heat pump thermostat. So we're trying to get to the bottom of the controls logic, and there's a little bit of a language barrier, and so we're going to report back as soon as we have the exact right answer. I've got 30 wiring diagrams going back and forth over the past couple of days trying to answer this question in time for the webinar because we thought we had it and then we didn't. So we're going to get there.
Okay. All right. Another one just came in. Again, if you have a question, you can pop it into chat or the Q&A. We're monitoring both of them. And we do have a little time here for questions. So now's your chance to ask. Do you think gas-fired absorption heat pumps would ever come into play for small commercial or residential?
Gas-fired absorption?
Yes, gas-fired absorption heat pumps would ever come into play for small commercial or residential.
I can honestly say I don't know. I'm thinking of absorber chillers, which is a completely different topic. It's an interesting question. Whoever wrote that question, shoot me an email. I'll try to get to the bottom of it for you. Because that one's a higher level question than the target audience here.
Okay. Well, this person said, will do.
All right.
All right. Can any furnace be paired with this heat pump for dual fuel?
The answer is yes. So on top, your furnace it's 2 devices laid on top of each other. The furnace is only a heating device, and the air conditioner is a completely separate circuit laid on top of it with a coil that's in the airstream of the furnace. So your typical air conditioning system is just a one-way system. It's for cooling only. The only difference between that and the heat pump, as far as that coil that goes on top of your furnace, is that it has a reversing valve. I mean, it's more complicated than that. It sees higher pressures and it's a heat pump coil, but you can pull out your air conditioning coil. You can remove your old 13-SEER AC, get rid of that. You can put a new same size heat pump coil on the top of your furnace, and you can put a new, just like those heat pumps that we saw on the north side of the house, that would be exactly what they would look like. Mm-hmm. And whether that's 2-ton or 3-ton, and we connect them up and boom. So for heating mode and the mild days, you'd be using your heat pump, and you can set your heat pump thermostat to switch over to gas whenever you like. So benefit in the summer, greatly improved. We're always talking about heating. In cooling, we're way more efficient than what most of us have. I have a 13-SEER Carrier AC at my house, and I need to replace it. I don't need to replace it, but I'm going to replace it with a heat pump.
And I'm sure you know a guy who can do that.
I'm aware of a guy who could do
that. All right. Well, thank you everyone for your questions today. We've reached the end. So, oh, sorry. Okay. Yes, I will. Thank you. Sorry, something came through, but it was more of a note for me. Anyway, thank you all for attending. We are going to make a recording of this webinar available soon. In the meantime, if you have any questions, you can reach out to us via our websites. That's allseasonheatpump.com and airflowreps.com. Thank you so much. Tom, thank you for leading this today.
Thanks, everybody. See you again soon.
Bye. Take care. Stay warm.